Okay, good afternoon, everyone. It's nice to see you in our virtual world again. I hope you are doing well and your families in these challenging times. Um, First off, if you can hear me okay, please type yes into the chat window. Okay, thank you very much. Okay, gang. So before we get started with our traditional lecture, I noticed that a few of you have already logged into the ClassMarker website and successfully taken the lab exam. That's wonderful. If you haven't, please do that by the end of the day. You have until midnight to complete the online lab exam at the ClassMarker website. As always, if you have any technical problems or issues, shoot me an email and describe to me what's going on, and I'll do my best to get it taken care of for you. Also, you may have, if you do take the exam, you won't immediately get your complete final score because I have to go in and manually grade some of the questions. So when I'm finished with that process, I'll let you know that you can log in to get your final score on the lab exam. So before we cover anything else, do you have any questions right now about the lab exam or what's happening today? Anything related to the semester? Okay, everyone's quiet, so I'll take the silence as hopefully that you're all doing okay, and I certainly hope that you are. Okay, so gang, what we're going to do is continue our conversation in chapter 10. We were talking about the two categories of hormones that exist in the endocrine system, lipid soluble and water soluble. And at the end of last class, I was doing a little sketch where I was showing you how insulin impacted a liver or skeletal muscle cell. So I'm going to continue that conversation. And so you may want to, have your notes from last time and the drawing of the cell that you did. I'm going to continue with that. And hopefully it will make sense. So just one moment and I will start sharing my screen to bring that drawing up again. Okay, so at this time, you should be seeing my typically poor drawing of a cell with insulin. And if you have any questions or you can't hear me, please type into the chat window and I should get your message. Okay, gang. So we were doing a case study of insulin, right? I'm circling around the top of the screen right now with my cursor. We're doing a case study on insulin. So you get a feel for how insulin influences the physiology of a cell. So remember, our starting point is that we're assuming that you've eaten a meal. It could have been anything. And anytime you eat a meal, your blood sugar naturally goes up. Your body detects that and it releases some insulin in the hopes that it can lower the blood sugar. So exactly how does that work? This is what this diagram is all about. So let's review. Number one, we have insulin, which I'm drawing as a symbolic letter I inside a triangle. Insulin binds the insulin receptor on the surface of the cell. Okay, remember your notes from last time that insulin, like all water-soluble hormones, is not able to pass through the plasma membrane of the cell. So insulin is actually going to bind on the surface of the cell to the insulin receptor. Okay, so what that means, just bear with me a second here, is that insulin attaches to the insulin receptor. Now you've heard this from me many times. I'm going to say it again. when insulin binds the insulin receptor, it will activate an enzyme that's attached to the underbelly of the insulin receptor, because when insulin binds the insulin receptor changes shape. And when the insulin receptor changes shape, it activates an enzyme to convert ATP into cyclic AMP. Okay? This is what our notes are saying over here on the left side. Insulin binds the insulin receptor. That causes an enzyme called cyclic adenylase to convert ATP into cyclic AMP. And at that point, cyclic AMP is considered the first messenger because it is made in response to insulin binding. So before I go any further, do you have any questions about this scenario that's in front of you right now? Okay, all right. Please feel free to unmute your microphone if you need to say something or type something into the chat window. That is okay, and I want to encourage you to do that because I want you to understand, okay? All right, so next. Now, we recall from last time that I talked to you about these words acute and chronic, and the fact that every hormone is able to create acute and chronic responses from the cell. And we said that a chronic response was a long-lasting response. Like if you have chronic back pain, it just doesn't go away. It lasts forever. Okay? So a chronic response is a long-lasting response, whereas an acute response is a short-acting response from the cell. And I'm going to show you how that works now with the cartoon that's in front of you. Okay, so one thing to keep in mind is that in a scenario like you see in front of you, the cell is going to have these molecules, which I'm just going to designate with arbitrary letters. I'm just going to say A, B, C, D, okay? And what's important to appreciate is that when cyclic AMP is made, it's going to float over and attach to molecule A and activate molecule A. And what I mean by that is cyclic AMP binds to molecule A, changes the shape of molecule A, and turns it on. And when molecule A gets turned on, it goes over and it interacts with molecule B and turns that on. And then when molecule B gets turned on, it goes over and activates molecule C. And you're starting to see this billiard ball response. If you're used to playing billiards or pool, you know, if you hit one ball, it bounces off the next ball, it bounces off the next ball, it bounces off the next ball. That's what's going to happen here. When cyclic AMP is made, it will bind to molecule A and activate it. When molecule A is activated, it activates molecule B, which activates molecule C, which activates molecule D. Okay? Now, what we have sitting over here, embedded in the plasma membrane, is the GR. Is the GR. That wasn't very good. Let me try to erase that for just a moment. Where is my pens? Oh, there we go. Okay. So, gang, over here in the plasma membrane is the GR. Please type into the chat window what you think GR is. What do you think GR is? Any thoughts? What do you think GR is in the drawing? Well, gang, what do you think insulin is doing when it causes a liver or skeletal muscle cell to respond? What happens? What's going to happen to the body when insulin creates an effect in the body? All right, maybe we need to back up here. Okay, let's come over here. Let me ask a new question. Why does the body release insulin? If you think you know the answer to that, please type it into the chat window. What's the purpose of the insulin? What's happening here? Okay, so Kira says decrease glucose in the body. Abigail, is it to maintain homeostasis? Alexi, to control blood sugar. Well, you're all hitting it pretty well, and that's exactly correct. What does insulin do? It lowers blood sugar. It lowers blood sugar. And your answers hint that you appreciate that. So, what do you, with that new information, what do you think GR is? It's not a hormone. Okay, what is the most common form of sugar in the body? There you go, Abigail. Glucose receptor. That's exactly right. GR is the glucose receptor. Okay, glucose receptor. Okay. All right, so let me ask you another question here, okay? And I'll put it in the chat window. If blood sugar, meaning glucose, is high, where does it go when insulin is released into the bloodstream? If blood sugar, glucose is high, where does it, meaning the glucose, where does it go when insulin is released into the bloodstream? So the next question I'll sketch on the pad is, what does lowering blood sugar mean? What does that actually mean? Okay, Alexi says it goes to your muscles as glycogen and is stored as fat. Well, you said some good ideas there, Alexi. It won't necessarily be stored as fat because glycogen is not fat. So, Alexi, stay with me here because you're on to something. Alexi,
I know, I said, and when it goes to the muscle, it's stored as ATP.
Okay, so Alexi, for it to be stored, does that mean that the glucose has to enter the cell?
Right.
Okay, thank you very much. That's exactly what I wanted out of you. Okay, good job. Okay. So what does lower blood sugar mean? It means that the sugar that's in the bloodstream enters the cells of the body, the skeletal muscle cells and the liver cells. That's what lowering blood sugar actually means. The sugar enters the cells. Okay, so up here, where we have the glucose receptor, remember that outside the glucose receptor, we're going to have a bunch of glucose. Okay, and I'm not very good at drawing, but let me just put some dots here. And we're going to say that all of this is glucose. Okay, this is glucose that's in the bloodstream. Honestly, it's the interstitial fluid, but don't worry about that right now. Okay, so let's think about it. This glucose right now that I'm circling with my pen or pencil is high in the body in the bloodstream because you ate a meal. So your pancreas releases insulin and pushes it into the bloodstream where it circulates around and comes near a liver or skeletal muscle cell. So the insulin binds the insulin receptor, changing the shape of that receptor so that the enzyme cyclic adenylase converts ATP into cyclic AMP. Cyclic AMP is the second messenger. It's called the second messenger because it's like the second man in a relay race. The first man was insulin, but because the first man carrying insulin can't get through the plasma membrane, you have to change the baton to the second runner, which is the second messenger cyclic AMP. Cyclic AMP is the second runner in our relay race. So cyclic AMP activates molecule A, which activates molecule B, which activates molecule C, which activates molecule D. And the short take-home message from this, if I can get my pen to work, is that molecule D will go over and it will bind and change the shape of the glucose receptor and turn it on. So the glucose receptor is opened up in response to molecule D binding to it. And when that happens, the glucose that's sitting outside the cell is going to come into the cell. Glucose enters. Glucose enters the cell. Okay? So if glucose enters the cell, hopefully you can see that we have in fact lowered the glucose level outside the cell. We have lowered the glucose level in the bloodstream. Before I go any further, questions? All right. Now, it's important that you begin to appreciate what this acute and chronic business is all about. So let me ask you a question, and I suppose I'll just type it into the chat window. That way everybody can potentially respond to it. And I'm speaking, my question is going to be strange, but I want to use an analogy with you. Okay, I want to use an analogy. If you were going to buy a home, could you move into your home faster if you purchased a pre-manufactured house or one that had to be constructed? Okay, here comes the question. If you were going to buy a home, could you move into your home faster? I repeated myself, sorry. Could you move into your home faster if it had to be constructed or was already made? Okay, pre-manufactured. That's my point. That's my point. You hit it right on the head. Okay? These molecules that I'm going to highlight at this time, hold on, let me get a different color here. these molecules that I'm going to highlight right here, the glucose receptor, molecules A, B, C, and D. These are like a pre-manufactured house. The cell already has them in place and can rapidly respond to an order from insulin to do something. So because these molecules are already in place, they can create a rapid short-term response from the cell when they receive the information from insulin. So you should consider everything in yellow as part of the acute response. Okay? These molecules are already in place in your cells because Mother Nature expects that every so often your blood sugar is naturally going to go up because Mother Nature knows that you have to eat every day. Every day you're going to have, 2 or 3 meals. You're going to have a breakfast, you're going to have a lunch, hopefully you're going to have a dinner. And so every once in a while your blood sugar will go up. And so Mother Nature made some pre-manufactured homes, some homes that are already built, they're already in place to handle the emergency of blood sugar going up. Okay? So these molecules of the acute response can in fact respond to insulin rapidly to bring glucose inside and lower blood sugar. Do you have any questions right now? Okay. Now here's the deal. Your body also has the ability to adapt to unusual circumstances. And here's what I mean by this. Let's say before the next exam in the course that you get a little bit nervous about the fact that you're going to be taking an exam. And so you go out and purchase 6 packs of Twinkies or cupcakes and you eat all of them. Well, obviously, if you eat 6 packs of Twinkies or cupcakes and you eat all of them at one time, your sugar level is going to go through the roof. It's going to go really, really high. And so your body will release insulin after you eat your 6 packs of Twinkies, and your cells of the body will use the machinery of the acute response to bring your blood sugar down. And that'll work okay. But let's say next week after you've taken your exam, you're sitting at home resting on your sofa, and you think back over your day, and you think to yourself, wow, I really enjoyed the sugar rush I got from eating 6 packs of Twinkies. In fact, I enjoyed that sugar rush so much that, you know what? I think I'm going to start eating 6 packs of Twinkies every day at lunchtime. Now, obviously, this is an over-the-top example, but my point is this. You know that eating 6 packs of Twinkies every day at lunch is not a healthy diet. Your body is not going to like that. And if you do that, you're going to create a tremendous amount of biochemical stress on the cells of your body so that your cells could actually wear out and die. And so if you start eating 6 packs of Twinkies every day in an unusual diet, the cells of your body are going to start to get very stressed out. Okay, they're going to try to use the acute response to lower blood sugar every day, but because you're eating this horrible diet every day, the machinery of the acute response is going to start to wear out. It's kind of like wearing a sweatshirt for 1,000 days in a row. Imagine what your sweatshirt would look like if you wore it for 1,000 days and you were washing it constantly. It would simply fray at the ends of the sleeves. It would wear out. So if you eat an unusual, unhealthy diet, your cells have to adapt or they will become damaged and potentially die. This is where the chronic response comes into play. The chronic response, okay, let me get a different color here. The chronic response is an adaptation response. Chronic response to an unhealthy diet. Okay, so let's say that you start eating 6 packs of Twinkies every day, and it starts creating a great deal of stress on the cells of your body, the liver cells and skeletal muscle cells in particular for our conversation. So what's going to happen is that the level of glucose, because of this unhealthy diet, the level of glucose is just absolutely off the charts. Okay, so the amount of glucose out here just keeps going up and up and up and up and up because of all the Twinkies and cupcakes that you're eating. It's very unhealthy. Okay, so think about it. The glucose receptor we have here is like a doorway. And this is the only doorway we currently have to bring sugar into the cell. That means the more glucose we have outside, if we only have one door to get it through, it's going to take a lot longer to bring the sugar level down in the bloodstream. The longer it takes to bring that level down, the more inflammation will start happening in your body. So to combat that, your cells will respond with the chronic response. And what that means is this. Okay. Okay. What that means is, in order to handle the new unusual diet, your body, the cells of your body, including the one that's drawn in front of you, as the acute response begins to wear out, as it becomes biochemically fatigued, one of the molecules is going to enter the nucleus. Okay, so here we have the nucleus. And you know that in the nucleus, you have this thing called DNA. Excuse me. So what's going to happen is that one of these molecules during the chronic response is going to go into the nucleus. It's going to physically attach to the DNA at certain locations and activate the expression of genes to help the cell bring sugar into the cell faster. Okay, so as an example, molecule B would come into the cell, bind to the DNA, and activate the expression of genes to make more molecules A, to make more molecules B, to make more molecules C, to make more molecules D, to make more glucose receptors. So the chronic response means that genes are turned on. Genes are turned on to allow the cell to bring sugar in faster. Okay. So if we have, just as an example, if we have 2 additional glucose receptors that get made in response to the chronic adaptation, that means I now have 3 doorways that the glucose can enter the cell. I have 3 doors to bring the glucose in rather than 1 door to bring the glucose in, means I can get the blood sugar down just that much more rapidly so that I don't create inflammatory processes in the bloodstream. This benefits your body by reducing the inflammation in the bloodstream. Okay, so it's hard for me to know whether I'm reaching you on this. So gang, what questions do you have? Do you understand my notes at this time? Is this making sense, gang? Tell me how I can help you. Okay, so the part of the insulin response that involves manufacturing new molecules is actually the chronic response. The part of the response that involves turning on the genes is the chronic response. Turning on the genes is going to take some period of time to get working. Okay, so, but once we do that, once we turn on the genes, we now have additional molecules that can last for a long time in order to handle this new, very unhealthy diet that you've chosen to eat, which is 6 packs of Twinkies every day. So the point of it is that the cells of your body can adapt from an acute response back to a chronic response, and from a chronic response back to an acute response. For example, let's say you started eating 6 packs of Twinkies every day. Then your cell is going to respond by making more glucose receptors, as I've drawn here. But let's say after 4 months of eating 6 packs of Twinkies, your friends that care about your health and well-being pull you aside, give you a swift kick in the rear end and say, hey, what are you doing to yourself? That's a really bad diet. And so after 4 months, you stop eating 6 packs of Twinkies every day. If you stop eating 6 packs of Twinkies every day, your blood sugar's not going to be as high as it was, which means you don't really need these extra glucose receptors anymore. And if that's the case, what your body will do over time, it will take those extra glucose receptors that it doesn't need anymore, and it will get rid of them. It will break them down, and you will return to the original state of just having one glucose receptor. So the point of our conversation is that depending on the environment, depending on the diet that you choose or don't choose to eat, your body can adapt to increase its sugar intake ability or lower its sugar intake ability, depending on the kind of diet that you're consuming. Okay. Let me walk through this one more time, just so I know I've covered it with you, gang. Okay? One more time from start to finish here. And the reason I'm doing that is because I know there's going to be an essay on the upcoming lecture exam on this topic. Okay, so I wanted to show you how insulin, which is a water-soluble hormone, can change the behavior of a cell. And a typical example, when insulin is released in response to elevated blood sugar because you had a meal or something, the insulin binds to the insulin receptor embedded in the plasma membrane, changes the shape of that receptor so that another enzyme converts ATP into cyclic AMP. Because cyclic AMP was manufactured in response to insulin binding to the receptor, we call the cyclic AMP the second messenger. The second messenger, cyclic AMP, binds and activates molecule A, which activates all these other molecules in a ping-pong style fashion. Molecule B opens up the glucose receptor, glucose comes inside, and we've lowered blood sugar. All of that can happen very rapidly because everything in yellow here is part of pre-manufactured housing, pre-manufactured machinery that is able to respond to insulin binding rapidly, do what it needs to do, and then shuts off. In the case where you start abusing your body with a very unhealthy diet, eating lots of sweets and sugars, which you should not do, the cells of your body will try to adapt by using the genes in the nucleus to manufacture additional glucose receptors to bring even more sugar in rapidly to prevent inflammation from happening in the body. When you alter the expression of the genes in the DNA, that is now a lasting response, a chronic response of the cell. Gang, do you have questions? Is it possible to type these steps out into 2 different scenarios? Okay, let's do a little bit of that on the Word document. Okay, let's see here. I'm going to shrink the picture, bring up the Word document. Okay. Let's see here. I'm going to increase my font a little bit. Hopefully you can see it. All right, so insulin drawing. Insulin is released from pancreas because blood sugar goes up after a meal. Okay, let me see. I got to do something to get all of that on one screen for you. Okay, let me know if you're having trouble seeing things. Insulin is released from the pancreas because blood sugar goes up after a meal. Insulin binds the insulin receptor, causing production of cyclic AMP, which is now called the second messenger. Cyclic AMP activates pre-existing molecules in the cytoplasm that are pre-made by cells to handle the normal spikes in blood sugar associated with healthy meals. The end result of this is that the glucose receptor opens up and brings glucose inside. Glucose receptor opens and glucose enters the cell. Okay, so steps 3 and 4, and what I've circled in the drawing, are part of the acute response. Because we're using molecules that have been pre-manufactured and are pre-positioned, if you will, to respond to blood sugar spikes. If you start eating an unhealthy diet and think, 6 packs of Twinkies. I don't even know if they make Twinkies anymore. Do they? Do they make Twinkies? I don't know. But if you start eating 6 packs of, sugary cupcakes or whatever it might be, you start eating an unhealthy diet, the machinery of the acute response will start to wear out. The machinery of the acute response will start to wear out. This puts biochemical stress on the cell. Okay, this biochemical stress could kill the cell. And for the cell to avoid dying, the cell has to adapt. So to avoid death, the cell must adapt. Okay. Part of the cellular adaptation here is going to be that one of the pre-existing molecules in the acute chain, one of the molecules in the acute machinery chain, if you will enter the nucleus and activate gene expression, turn it on. Will activate gene expression so that additional machinery capable of bringing sugar into the cell is made. Once again, one of the molecules in the acute machinery chain will enter the nucleus and activate gene expression so that additional machinery capable of bringing sugar into the cell is made. This manufacturing will take a little bit of time, but once it's completed, the capacity of the cell to bring sugar in is increased. And by doing that, we lower the stress on the cell and on the body. And this change in status, where we had to make more molecules to do this, is part of the chronic response. Okay. Step 6 is part of the chronic response to lower blood sugar and to lower stress on the cell itself. Okay. What else can I do for you? What else would be helpful? What questions do you have? Is there anything you'd like to ask at this time? Okay. All right. Okay. I know it's difficult to think about it in these terms when it doesn't seem like it, but folks, our cells really are very miniaturized biological machines. The kind of machinery you might think of when you look at an engine in your car running. The inside of your cell is really not so different. Okay. Yes, I will send this Word document with the video later so that you will have it. Okay. Anything else before we continue? Is the chronic response associated with diabetes? Yes, it is. And usually the chronic response, when you progress to actually being diabetic, usually even the chronic response is starting to fail, so that the body simply can't keep up with the sugar levels in the bloodstream. And I do intend to talk about diabetes in just a few moments. Other questions? Okay. So Kira, to your question, the chronic response does not cause diabetes, but when the cell becomes overwhelmed so that even the chronic response is not capable of handling things, then we can actually develop diabetes. Okay. All right, gang. So since it's sort of come up a little bit here in questioning and conversation, let me just point out at this time, your lecture exam 2 is coming up next Monday, right? Today, you must take your lab exam online. Please take your lab exam before midnight. Next Monday, you have your second lecture exam. Typically, if I was with you in class, I'd be giving you your study guide on the board. However, today, because not everybody is online and people have very different schedules right now with the new realities we're dealing with the emergency, I have typed up the study guide on a Word document, and I will be sending you the study guide this afternoon, at least before the end of today. You will have the study guide for lecture exam 2. Just like I've done in the past, in the study guide, you're going to find vocab words that I tell you that you need to study and prepare for. And I give you a hint about the essay questions that you're going to have to answer on next week's exam. Okay? So note to you, in the Word document, you will receive the exam 2 study guide by email later today. Okay? Do you have any questions about exam 2? I mean, I'm not going to go over the study guide right now because I have other things to do with you, but do you have any other general questions about what's happening right now? Okay, all right. So let me make my window here bigger. So hopefully you can see everything better. And gang, I have to pick and choose how I'm going to spend time with you. And so what I'm going to do at this time is give you some examples of other hormones. I will not go into the same detail I did with insulin because there's just no time, but I want to make you aware of some hormones and things that I bet you've heard about. And if you haven't, well, then this would be new ideas for you. So, examples of other hormones. Okay, first off, let's list the organ or tissue that creates some of these hormones. We're going to talk about the pituitary gland, okay, which you may be aware of is in your brain. And you see it, you actually do see it on page 175 with the picture of the woman there. And also the pituitary gland is highlighted on page 173. Okay. Now, I'm not going to hold you responsible for all these hormones, but any hormone that I put into your notes here, you are responsible for. So let's have an example here. Okay. The pituitary gland is responsible for producing growth hormone. Okay. So growth hormone is the hormone that causes the cartilaginous growth plates, the epiphyseal growth plates of your bones to grow and get bigger. Okay. So the growth hormone stimulates growth of your bones by causing cells in the growth plates to reproduce, to number one, reproduce, in other words, perform mitosis and increase the number of cells present, and number two, to increase their volume. Okay, so question coming into the chat window. If a cell increases its volume, what topic, what process must be involved? If a cell increases its volume, what process must be involved? Okay, fantastic. Osmosis, right? I mean, if you want to make a balloon larger, what do you got to do? Put more air into it. If you want to make a cell larger, what do? You got to put more water into it. So, you know, it might be a strange thing because we talked about osmosis some time ago, but osmosis is still extremely relevant to topics that we are currently talking about in the course. Okay, so growth hormone is one hormone that does that. And I wanted to make you aware that there are some growth hormone deficiencies and disorders that have been characterized by medical science. If you have too much growth hormone, during the childhood years, then you can develop into a pituitary giant, so-called. You will have giantism. Okay, and if you know who I mean by Andre the Giant, then you know what giantism looks like. There's also a picture on page 177 of your textbook with Robert Wadlow, figure 10.7, that shows you an example of a pituitary giant. That gentleman reached a height of 8 feet 11 inches tall. That's insane. Now, as kind of cool and neat as that seems, please understand that his health was very poor because the human body did not evolve to become that tall. The taller you are, the more blood vessels you have, the harder it is for your heart to move blood throughout all of your tissue. So being that tall might look neat, but it comes with a lot of health consequences with it. Okay. If you have too little growth hormone, during the childhood years, then you will have pituitary dwarfism. All right. And yeah, there is a pituitary dwarf on page 178, figure 10.9. Finally, it's important that you know it is possible actually to produce too much growth hormone during the adult years. And since you've already stopped growing taller, the consequence of having too much growth hormone during the adult years is to make the bones of your body abnormally thick. Too much growth hormone during adulthood leads to a condition called acromegaly. One moment, please. What do you need? Okay, all right. All right, sorry, folks. I got a 6-year-old that I'm babysitting right now. Okay. So, all right. So any questions about growth hormone? Okay, let's continue here. I'm going to have to go a little bit faster to be sure that I cover the content with you. Some other hormones produced from the pituitary gland that may be of interest. We have prolactin. Okay, prolactin is the hormone that stimulates the mammary tissue in women to produce milk. Okay, prolactin is the hormone that stimulates milk production in the mammary tissue. Question coming through the chat window. Are men capable of producing milk? Abigail says in rare instances, and she's exactly correct. Men have all the functional anatomy necessary to produce milk, but because of differences in hormones, typically do not produce the milk. But it's pretty common these days to have a male baby born because the male baby was exposed to the mother's hormones in the mother's bloodstream. A lot of times baby boys, when they're first born, actually produce a little bit of milk from their mammary glands. In addition to that, there have been documented cases of extreme stressful conditions that men have been under, such as, you know, when men have been prisoners of war, such as, say, during Vietnam and things like this, when men have been prisoner of war and they've been under very harsh conditions, that the stress of that circumstance changes the hormonal production in the male body. And there's been documented cases of prisoners of war actually producing milk from the mammary tissue because of these extremely stressful times. So long story short, yes, men can produce the milk, it's just we usually don't. Okay. Another hormone is, let me see here. Another hormone is oxytocin. Oxytocin is a hormone that does a couple, well, it does several things, but what I'm going to tell you here is oxytocin stimulates uterine contractions during childbirth, and it stimulates the mammary tissue to eject milk to nurse the child. Stimulates uterine contractions and stimulates mammary tissue to eject milk to breastfeed a newborn. The reason I'm bringing this up is because take a look. Prolactin is a hormone that stimulates the mammary tissue to produce the milk, and oxytocin is a different hormone that stimulates the mammary tissue to eject the milk. That's a very common theme in the endocrine system where you have two different hormones that regulate different aspects of a common theme, right? two different hormones that regulate production and release of a substance. Okay, that's what we're showing you here. Prolactin and oxytocin are two different hormones that regulate production and release of a substance, in this case, milk. Okay, another hormone. One that I want you to know about is follicle stimulating hormone. Okay, follicle stimulating hormone promotes the development of egg cells in women, and actually men. Follicle stimulating hormone stimulates the production and maturation of sperm cells in the testes. But at any rate, follicle stimulating hormone promotes the development of egg cells in women, and it stimulates the secretion of estrogen from the ovaries. Okay, so let's write that down and then I'll talk about it. Promotes the development of egg cells in women and stimulates the release of estrogen from the ovaries. Why I want to make a point about this one is that follicle stimulating hormone, or FSH for short, is a hormone that we call a tropic hormone. FSH is an example of a tropic hormone. The word tropic, as in tropic hormone, is a vocab phrase for you for your exam next week. A tropic hormone is a hormone that's released by one kind of tissue. For example, FSH is released from the pituitary gland, and it travels through the bloodstream, binds to cells in the ovaries, and stimulates the ovaries to release a second different hormone. That's what a tropic hormone is. It's a hormone released from one tissue that stimulates the release of a second hormone from a second different tissue. A tropic hormone is a hormone that is released from one tissue and stimulates a second tissue to release another different hormone. That's also a very common theme in the endocrine system, where you have one hormone causing the release of another hormone. Okay. All right, gang. Questions right now? Okay, I'm looking at our clock right now. It's almost 1:30, so I think what I'm going to do is talk to you a little bit more about insulin and its relationship to diabetes. So, okay, so we've been talking here about the pituitary gland. There's plenty of other structures in the body we could talk about, but let me mention the pancreas. Okay. The pancreas can release insulin, as you know, and the purpose of insulin is to lower blood sugar. It lowers blood sugar through the mechanism that we spent considerable time drawing in the PowerPoint slide and taking some notes on. So insulin lowers blood sugar, and glucagon raises blood sugar. Okay? So think of your sugar level as being a seesaw at a playground. A seesaw. You know, that normally you want it to be balanced, but every once in a while it dips down on one side and the other side goes up. And then the other side goes back down and the first side goes up. Your body has to have the ability to lower blood sugar and, when appropriate, to raise blood sugar. Okay, so let's see here. Let's see. Let's define diabetes mellitus. Okay, diabetes mellitus is a group of metabolic disorders characterized by abnormally high blood sugar levels. Okay, so question. What is healthy fasting blood sugar supposed to be? Can anybody type that into the chat window, type an answer in? What is healthy fasting blood sugar supposed to be? By fasting blood sugar, I mean, what should your blood sugar be in the morning when you've been asleep for 8 hours and you wake up before you eat breakfast? What should your blood sugar be? Does anybody know? If you don't know, it's okay, but if you don't know, think about it, how much you take it for granted that your body works properly. Okay, thank you, Terry. Terry, that's a fine range. There's actually, you know, depending on what textbooks you read and everything, you might get a little bit difference in that number. So Terry says 100 to 125. That's not a bad answer, Terry. I'm going to say just a little bit of a different range for you. I'm going to say 90 to 110. Now, what are my units? What are the units for that? Does anybody know what the units would be? Millimoles? No, not millimoles. Okay, so gang, the units are going to be milligrams of glucose per 1 deciliter of blood plasma. 90 to 110 milligrams of glucose per 1 deciliter of blood plasma. That's the units. So when you wake up in the morning, your blood sugar should be in that range. If it's significantly higher than that, you might be diabetic. Okay. All right. So a couple other questions we should answer here before we get into the nitty-gritty detail. What condition is more immediately dangerous? Low blood sugar or high blood sugar? Okay, notice how I've worded that question. What condition is more immediately dangerous? Low blood sugar or high blood sugar? Please type an answer into the chat window. Okay, Kira says low. Does everybody agree with her? Okay, Terry says high, so he doesn't agree. Very good. All right. Well, the answer is, yeah, okay. Eileen, okay, very good. The answer is low because of the word immediately. Immediately. And here's what I mean by that. If you have low blood sugar, you could pass out and actually pass away if somebody doesn't help you. So having low blood sugar is immediately dangerous. If you have low blood sugar right now, that could kill you today. High blood sugar, on the other hand, is not immediately dangerous. High blood sugar is not going to kill you today. But if you have high blood sugar for the next 15 years, that could damage blood vessels and nerve endings and create disease that will kill you in 15 or 20 years. Okay, so low blood sugar is immediately dangerous, whereas high blood sugar is dangerous over the long haul of life. Okay, all right. So there's so many important aspects to diabetes. Unfortunately, we won't have time to cover everything, but I would like to talk to you about type 1 and type 2 diabetes mellitus. Okay. So, gang, we're going to talk about diabetes mellitus. There is another form of diabetes you may have heard about called diabetes insipidus. Diabetes insipidus is a problem with kidney function. It's much less common than diabetes mellitus. So, if I had a ton of time, I'd talk about it, but I don't have a ton of time. So I'm just going to talk about diabetes mellitus with you. We've already defined it above as a group of metabolic disorders characterized by abnormally high blood sugar levels. Okay. So, first off, everybody thinks that there's type 1 diabetes mellitus and type 2 diabetes mellitus. And while that's useful information, the reality of it is that there is certainly more than 2 types of diabetes mellitus. It's just that you don't hear about it because only the scientists and researchers doing this know about this. Okay? But there are many types of diabetes mellitus, more than just type 1 and type 2. Okay? So as I say that, but the reality of it is we don't understand all these different versions. It's still an active area of research that medical science is still trying to figure out. So let's talk about type 1 diabetes mellitus. Type 1 diabetes mellitus, you may know as juvenile diabetes. And that's because this form of diabetes often hits people, often occurs in childhood. Okay. Please be advised, though, that you don't have to be a child to have type 1 diabetes. You could be 47 years old and still have type 1. That is possible. It's just that it frequently does occur in childhood. It is possible for adults to have type 1. Okay. If I was with you, I would try to spend more time having you answer my questions for me, because I think that's much better than having you sit there and passively listen. But with our time being what it is, I'm going to give you some information here. Okay, type 1 diabetes is juvenile diabetes, and you may be aware, excuse me, I may sneeze. You may be aware that type 1 diabetes is considered an autoimmune disease. What other disease did we talk about specifically in this course is considered an autoimmune disease? Type that into the chat window if you know it. What other disease? All right, very good. MS, multiple sclerosis. Well, here you have a second one, gang. Type 1 is an autoimmune disease. In this scenario, the cells of the immune system get confused and attack the cells of the pancreas that make insulin. And because of that, you don't make any insulin. Type 1 diabetes, the pancreas stops making insulin, which means patients become insulin dependent. Okay. Pancreas stops making the insulin, so patients become insulin dependent, meaning that you need an external source of insulin through an insulin injection or insulin pump to provide the insulin to the body. Okay. Exactly what causes the immune system to get confused is still a considerable topic of research. We truly do not know, but some recent observations in the research world have implicated a previously undetected virus that may in some cases account for type 1 diabetes. So the story's still out on that, and I'd be happy to chat with you about during office hour or something like that if you're curious. Okay. So the pancreas stops making insulin, the patients become insulin dependent. Folks, do you have any questions about type 1 diabetes? Okay, not seeing any questions. let's talk about type 2. Type 2 diabetes mellitus is often referred to as age onset diabetes. And what we mean by that is the older you are, the longer you live, the more likely you are to develop this. Okay. Now that's not to say you couldn't be 13 and be a type 2. That does happen for a variety of reasons. But typically we see type 2 diabetes in older folks, you know, people in their 50s, 60s, 70s, that kind of thing. Okay. Now we'll come back to that about what it really means to be age onset. Okay. In this scenario, what seems to be happening in at least some subset of patients is that these patients become insulin resistant. So the pancreas is still making the insulin, but the cells of the body that should respond to the insulin don't respond anymore. Okay? It's kind of like talking to your teenager. They just don't respond. And so I'm going to ask you in the chat window. Well, I better put it in your notes because this is important. I want to ask a question here in the notes. Okay. Why do the cells of the body stop responding? You tell me, what do you think could cause a cell to stop responding? Why do the cells of the body stop responding to insulin? Okay, you should be able to give me at least one answer on that. We've been over enough of this at this point. Think about our conversation with the insulin drawing and the insulin example. Why do you think a cell might stop responding to insulin? Okay, Abigail says overexposure. So you think that this is an adaptation thing. That's a nice idea, but not in this case. Anybody else? Well, if you look back at your drawing, what part of the drawing shows what part of the drawing? Okay, I'm seeing your other answers. Thank you, folks. Nobody's quite hit it yet. What part of the drawing actually physically binds to the insulin? What part of the drawing binds to insulin? Okay. We're getting short on time. Thank you. Thank you. Yes, thank you for the answers. Exactly. The problem with type 2 that we most understand best is that this is an insulin receptor problem, where the insulin receptors are either missing, completely missing, or they're present, but they're mutated in some way. Okay? And so because of a mutated sequence in the protein, you get a mutated shape, so it doesn't respond to the insulin anymore. Why do the cells of the body stop responding to insulin? Because the insulin receptors are missing or mutated. Okay? And so I know we're at 1:45. I'm gonna finish this story, gang. If you have to go, I understand. But I'd ask you to stay with me another few minutes. Okay. So the insulin receptors are missing or mutated. You might ask yourself, well, why are they missing or mutated? And then the answer comes back to this phrase, age onset. Think about it. The longer you've been alive, the longer the cells of your body have been alive, the longer the cells of your body have had to reproduce themselves. And the more times you reproduce yourselves, the more likely it is you're going to make a mistake in copying the DNA you need to make a new cell. So simply being older means you've given the cells of the body more opportunity to do things, which means more opportunity to make mistakes. Okay, so over a lifetime of living, the DNA inside cells can accumulate errors, such as errors in the insulin receptor gene, causing the protein, meaning the receptor, meaning the protein, made from the gene to be abnormal and function abnormally. Okay? Because this is a genetic issue, there is no therapy, there are no treatments that can cure this at this time. Maybe down the road we will have some gene therapy treatments that could potentially correct this, but as of right now, there is no cure for these conditions. Okay. Gang, do you have any questions right now? I know that was pretty fast finishing things up. Okay, so here's what's going to happen. I will send you an email with today's notes, a YouTube link to the recording, your study guide, so forth. Okay, that'll happen before the end of the day. I will be online in about 15 minutes for an office hour. If there's any topics or concerns you want to talk about, I'll be online here and be happy to help you. And in the meantime, please continue to be safe. Take care of yourselves and your family. Do you have any final questions before we take a 15-minute pause? Okay. Then if I don't see you in 15 minutes, take care of yourself. Otherwise, I'll be back online at 2:05 for office hour. Okay, see you soon. Bye-bye for now. Hi, folks. For your review, my today's lecture recording. My today's lecture notes attached to this email. Hi, folks. For your review, my today's lecture recording, Chapter 6. Is it